Extreme physics.
All right, we had some stormy weather, but that doesn't mean we need to stop our learning. We need to keep learning. So let's take a look at a question from your book. It is a Newton's third law problem. And it's a typical problem where we have interacting objects. We have three masses. One mass is interacting with the table and the two strings, and these masses are just interacting with the strings. So let's take a look. We have the coefficient of friction with the between the table and the 2 kilogram block, and we want to know what is the acceleration of the 2 kilogram block. Okay, we have three objects. We want to know how the system moves. We're going to, of course, draw three free body diagrams like that. We're going to want to lay the free body diagrams out physically similar to the way that they are laid out in the problem. This will be 1. This one will be the 2, and this will be 3. It's convenient that they gave us these numbers that are sequential. In this direction, we have the weight down and the tension up. We have the tension of the string on 1, and here we have M1G down. All right, so we have that, and over here we have let's see, we have the tension of I'll call this string 1 because we have two different strings. String 2 on 2. We have the tension of string 2 on 2 this way, and we have the tension of string 1 on 2 that way. And we have the second mass times g. It's weight downward and upward. We have the normal force. Normal force of, I'll just call it normal force. It's a surface on 2. SUR on 2. Surface on 2. Upward. We have the coefficient of friction between surface and 2. Over there. We also have friction. If this thing's going to be accelerating this way, we also have friction, and that is going to be kinetic friction. Friction kinetic of on 2 is that way. All right. There we go. We have two forces associated with the surface, and we have two tension forces, and we have the weight. All right, over here we have the tension of string 2 on 3, and here we have M3G, the weight. We also need an acceleration constraint. How do these move? They move in some sort of relation to each other. This is going to accelerate that way. That one's going to accelerate that way. That's going to accelerate that way. So I'm going to say the acceleration of 1, that's positive. It's in the positive direction. The acceleration of 2 is also in the positive direction, and if this moves 2 centimeters, that moves 2 centimeters, so they're going to have the same acceleration. And then here we have the acceleration of 3 is going to be negative 3. It's going to accelerate downward while these others are accelerating in the positive direction. And there we go. There's our acceleration constraint. Certainly another valid one would be minus A1 equals minus A2 equals positive A3. Same thing. So anyway, there we go. We have our acceleration constraints. We're going to be able to get 1, 2, 3, 4 equations out of here. Here we have an equation, and we're also going to probably need to use our friction. And we're going to have a whole bunch of equations. I hope I can fit this all on the board. I may have to erase at some point. We'll see what happens. The sum of the forces on the 1 kilogram block equals mass 1, acceleration 1. Sum of the forces on the 2 kilogram block equals mass of the 2 kilogram block times the acceleration of the 2 kilogram block. This is in the x direction, or I mean, sorry, this is in the y direction. This is in the x direction. And then, of course, the sum of the forces on 2 in the y direction will equal 0. It's not going to accelerate up or down. So there we go. We're going to have those two equations and Newton's second law. And we have sum of the forces in the for 3 in the y direction equals mass of 3, acceleration of 3. All right, make sure everything's labeled. That's the key. We have a whole bunch of moving parts. We don't want to mistake and put something in the wrong spot or assume two accelerations are the same or something like that. We always need to keep track of all these different moving parts. Now let's take a look at our acceleration, or our Newton's third law pairs. We see that the tension, assuming this is a massless string, these will act as if they are Newton's third law pairs. Okay, the tension of the string on 1 is going to be the same as the tension of the string on 2, the first string on 2 anyway. So those will be equal in magnitude, not opposite in direction because of the pulley, but these are also act as if they are Newton's third law pairs. They aren't exactly because they're not in opposite directions because of the pulley, but there we go. All right, so we could just change this to, I could change this to the tension T1. Let's just call that T1, right? That'll be a tension of rope 1. And then this one we will call, so then this is also T1. Sorry, it's getting kind of tight for room, but anyway, got a small board. So here we have T2, and this will also be T2. All right, so what force do we have here? Upward, we have a positive T1 minus M1G equals M1A1. And then in the x direction, we have T2 minus T1 minus kinetic friction on 2 equals M2A2. All right, hopefully you can read that. In the y direction, we have the normal force. I'm just going to call it N because we only have one normal force in this problem. Minus M2G equals 0. All right, well, that'll be nice. Normal force equals the weight. Good. And then we have a T2 minus M3G equals M3A3. There are our equations. That, along with our acceleration constraint, along with our mu, should get us in pretty good shape to solve for acceleration of 2. All right, let's do a little simplification. I think let's solve this for T1, then we could plug it into there. So we have T1 equals, and let's get everything in terms of acceleration 2. Since we're solving for A2, let's get everything in terms of A2. So A1 equals A2. So we'll just say this is M1G plus M1A2. All right? There we go. And then let's go over to T2. Plug that in there. So we have a T2 equals M3G plus M3 times negative A2. I can't read that very well. Negative A2. Negative A2, because we're going to plug that in there because A3 and A2 are opposite in sign. All right, so we have our T1 and our T2, and then we're going to, all right, so we're going to, I think we're done with these guys. So we're going to kind of spread this one out. We're going to spread this out like that because we're going to do all the work in here at this point. M3G plus minus, I'll just say minus, M3A2 minus the whole quantity of T1, which is M1G plus M1A2 minus, oh, this is getting sloppy. Here, let's go like this. All right, so this is T2, this is T1, minus friction. This is kinetic friction, so it's going to be mu times the normal force, but the normal force is just M2G in this case. Kind of solve that equation there. And that equals M2A2. All right, kind of sliding down the slope, the slippery slope. Let's get all the A2s on one side, I guess. All right, so we'll send A2s over there, that side, over there. I'll start down here. Give me a little more room. M3G minus M1G minus mu M2G equals M2A2 minus plus M3A2 plus M1A2. There we go. All right, got all the A's on this side, all the non-A's on the other side. Nice and segregated. All right. So the G's can come out. So what do we have? We have M3 minus M1 minus mu M2 divided by M1 plus M2 plus M3 equals A2. All right, there we go. There's our, there's the basic, it's a 3. There's our basic equation. Now we can plug some numbers in and come up with a number. And here's the exciting box of answerage. There's the box of answerage. All will be known in the box of answerage. Here we go, so A2 equals 9.8 meters per second squared times 3 kilograms minus 1 kilogram minus 0.30 times 0.2 kilograms divided by 1 kilogram plus 2 kilograms plus 3 kilograms. All right, let's crunch those numbers. 2.29 meters per second squared. All right, I have a positive number. Would I expect to get a positive acceleration? Sure. Yeah, feeling good about that. Let's take a look at the general. Now the problem with this is we don't get a strong sense of, did we mess up? Did we mess things up? Did we make a mistake on our signs? Did we not look at this mess? It made that too small. Should have made that bigger, but didn't have room. So let's take a look at this equation. Let's see if this makes sense. Well, we know that acceleration in general equals the net force divided by the mass. The acceleration of the system. System all accelerates together, and the mass of the system is 6 kilograms. And we see that we do have 6 kilograms in the denominator. Good. We're looking good so far. And then on the top is the net force. Well, we have, on this system, we have GM3 is it's the weight of this thing. So that's the weight of this thing. And that's given us a positive. Yeah, sure, give us a positive force. And then we have the weight of 2, which gives us a negative force, right? It's pulling that way. That makes sense. And then we have some sort of frictionally thing, which is opposing, which it's applying a force that way. So this all makes sense, and that is a reasonable answer. I don't know whether it's right, but it's reasonable. All right. There's a Newton's third law problem. Hope you enjoyed it, and I hope the snow didn't cloud your vision of all this physicsy goodness. See you later.
Extreme fair zone.